Alright, in the previous video I talked about basic elements in the framework. In particular, we talked about a preference relation. In this video we will talk about utility function and utility representation theorem. So for motivation in economics, we often describe the preference relation by means of a utility function. So this function is a mapping from the consumption set x to real numbers. So the function is a real valued function. And there are two benefits from working with this utility function. The first benefit is this is a function, so we can apply several analytical tools such as calculus, derivative over integral to these functions. So that facilitates our analysis on consumers' behavior. Okay? And the second benefit is, although bundle x, so an element in this consumption set, is a L-dimensional vector, but its value, u of x, is a real number. Okay? So we don't have to, so with this utility function, we don't have to work with an L-dimensional vector. Instead, we can simply work with a scalar that is much more convenient. Okay? So utility function reduces down the problem, so the dimension of the problem from L to 1, so that is also good. Okay? But in order to work with a utility function, there must exist some relationship between utility function and preference relation. So in other words, utility function must represent the given preference relation. Okay? So this idea is formalized in the next definition. So function u, we formally say function u represents the preference relation if the consumer of our interest thinks bundle x is at least as good as bundle y, then u of x should be larger than u of y. Okay? So the function u must assign a larger number to bundle x to bundle y. Okay? And conversely, if function u assigns a higher number to bundle x, then consumer thinks bundle x is better than bundle y. Okay? So if these two statements are equivalent, okay, so they imply each other, then we say function u, this function represents the preference relation. Okay? So from this definition, what matters for representation is the order itself. Okay? So the order between x and y. So as long as u of x is larger than u of y, the function u represents the preference relation. So that simply means such a utility function is not necessarily unique. Okay, it's not necessarily unique, because once we assign some number to u of x, then if we assign smaller number to u of y, then this function u does the job. Okay. So more generally, if the function u represents the preference relation, and we have another function f, increasing function, and their composition, f of u of x, okay, let me call this function v, then v is another utility function, can be regarded as another utility function that representing this, represents the same preference relation. All right, so this result is immediate from this definition. So suppose that function u represents this preference relation. So we have this. Okay? And the given function f is an increasing function, any arbitrary increasing function. That means although we take this function f on both sides, making composition, inequality is not reversed. Okay? So we have this equivalently, f of u of x will be larger than f of u of y. Okay? So in other words, function v of x will be larger than function v of y. Okay. So if u represents this preference relation, so does function v. Okay. All right, so this representation has an ordinal property. Ordinal property. Meaning that the property is preserved under monotone transformation. So we usually call this composition okay, or monotone transformation. Yeah. So if one property is preserved under monotone transformation, so it is invariant, okay, it's still alive, right? So representation is still alive even after taking increasing function, so monotone transformation. Then we say that property is ordinal, okay? Otherwise, so it breaks down. If it breaks down, we say it is a cardinal property, okay? So from this definition, what matters is the order, right? So it means this function u is an ordinal utility, okay? We sometimes talk about cardinal utility because in the sense that the utility function attempts to quantify the level of happiness or level of satisfaction or well-being by consuming some bundle, right? But at least for representation, it has a ordinal property. All right, then one follow-up question that arises is, we may wonder under which conditions we have such a utility function, okay? So that is called the utility representation theorem in economics. So now we are looking for some conditions under which, some given preference relation is represented by a utility function, okay? Now, one simple observation is when the consumption set is finite, okay, and we can easily find such a utility function under just one condition, that is, preference is rational. Okay? So suppose that one consumer's preference relation is rational, so it is complete and transitive, and consumption set X is finite. So it has a finite number of bundles like this. So it has only 3 bundles, okay, X, Y, Z. Then if his preferences are rational, then he can rank these bundles according to his preference. So he may prefer bundle Y the most, and bundle Z the second most, and bundle X the least, okay? Then in order to find the utility function representing his preference, okay, we can simply find the 3 numbers, say A, B, C. Okay, A is the highest, second highest. Also, A is the highest, B is the second highest, C is the lowest. Okay, and then we can just assign these numbers to each bundle like this. Okay, and let me call this function u. Okay. And this function u will represent the given consumer's preference relation. Okay. So rationality is a sufficient condition for existence of a utility function when consumption set is finite. Okay? And rationality is also, remarkably, rationality is also a necessary condition, meaning that if one consumer's preferences are not rational, so irrational, then we can no longer find such a utility function. Right? The reason is, suppose that one consumer's preference is not complete, so it's irrational. Okay, so that means given 2 bundles, say X and Y, the consumer can't tell which one is better, right? So although we have 2 numbers A and B, and we assign some number number A to bundle Y, okay, and the consumer resists to assign this number, the left number B, to bundle X, okay, because he does not know which one is better, right? That means, so it is left, like this. So we can't assign some element in the domain to real numbers. Then it is not a function anymore, right? So we don't have a utility function. So if the preference is incomplete, we can't make a function between these 2 sets, okay? So consumption set and real numbers. And transitivity, the next assumption on the rational preference, is immediate from the fact that real number system is also transitive. So if A is larger than B and B is larger than C, in the real number system, automatically A is larger than C. Okay, So if the consumer prefers X to Y and Y to Z, okay, and if we have a utility function U representing this preference relation, then U of X must be larger than U of Y, and U of Y in turn larger than U of Z, okay, and these are real numbers, so U of X must be larger than U of Z, yeah? So it must be transitive, okay. So transitive is immediate from the fact real number system is also transitive, yeah. All right, so so let me call this theorem the first version of utility representation theorem. So it tells us if the consumer faces a finite number of bundles, okay, consumption set is a finite, then for existence of utility function, what we need is a rationality. Rationality alone also guarantees the existence of U. Okay, so, but if we go beyond a finite consumption set, so if we consider infinite number of bundles, okay, then rationality alone does not guarantee existence. Yeah. So the counterexample is given by these lexicographic preferences. This is a very classic example. I believe you guys have seen this preference when you studied undergraduate microeconomics. But let me remind you of this preference. So if one consumer has a lexicographic preference in two commodity space, so we'll just consider two goods, good one and good two, then the way to rank the two bundles, okay? So now bundle X has just the two numbers, X1 and X2, and so does bundle Y, okay? And if the consumer has a lexicographic preference, he first compares the amount of the first good, okay? So if X1 is larger than Y1, so bundle X has a more of first commodities, then he prefers this bundle, okay, bundle X. And if two bundles have the same amount of the first bundle, the first commodity, then now he compares the second commodity. So if bundle X has more of the second commodity, he prefers bundle X, okay? So, the way to rank bundles is more like an alphabetic order. So this is why we call this lexicographic preference. He first compares the first good, yeah? And if only when these two bundles have the same amount, then he compares the second commodity, okay? So for example, 3,1, from his perspective, okay, if he has a lexicographic preference, 3,1 is better than 2,1 million. Yeah? So although bundle Y has a many second goods, yeah, I mean the consumer does not care. Okay. Okay. So one property of this lexicographic preference is, so if one consumer has a lexicographic preference, then his exchange ratio, okay, exchange ratio of these two commodities, in other words, marginal rate of substitution, MRS, is undefined. Okay, so remember the definition of MRS. So if MRS is 2, then we can see his exchange ratio is 1 to 2, right? So he is willing to give up 2 units of the second good in exchange for getting 1 unit of the first good, right? But in this case, lexicographic preference, he does not care about the second good. He first cares about the first good, right? So yeah. So if the consumer is crazy about the first good, just as people nowadays are crazy about real estate, then it's more like this lexicographic preference. All right, so you can easily check by yourself this preference is rational. Given any two bundles, the consumer can tell which one is better, and it is a transitive. Yeah. Nevertheless, however, this lexicographic preference cannot be represented by any utility function. Okay, so the way to prove this is a little bit technical, but might be intuitive. Okay, so let me prove this. Okay, so just compare these two bundles, 1, 0 and 1, 1. Okay, then by this definition, lexicographic preference, we can say 1, 1 is better than 1, 0. Okay, and suppose that we have function u representing this preference. Then u of 1, 1, u of 1, 1 is number d, and u of 1, 0 is number c. Then c should be lower than number d, right? And then we need a reference point, so 0, 0. 0, 0 and 0, 1. Okay, so I'd like to assign number 0 to 0, 0. Okay, and 0, 1, say this is a number a. Okay, so this is number a. All right, so u of 0, 1 is a, and u of 0, 0 is 0. Yeah. All right, so a is a strictly larger, so a is a strictly positive, right? So a is larger than 0. All right, then, so the problem is between 0 and 1, okay? So between these two pairs, we have infinitely many pairs, right? Say 0.50 and 0.51, okay? And 0.4, 0, 0.4, 1. There are infinitely pairs between these two. Okay, so by comparing, so in order to compare these two bundles, we need some positive measure a and 0. Okay, we need some positive number a. Okay, so we already piled up measure a. Okay. For the next bundle, for the next pair, we may need some another positive measure, right? And there are infinitely many, uncountably many bundles between these two. So stacking up those measures, inevitably will surpass this number d. Okay, so this number d will approach infinity. Okay, so we can't help assigning infinite number to 1, 1, right? So then what about a 1, 1.0? Also 1.1, 0. That is better than 1, 1, right? So we can't assign some real number to the next bundle. So that's why lexicographic preference has no utility function, right? In case of infinite consumption set. All right, so the previous example tells us in case of infinite consumption sets, utility representation calls for another assumption on the preference. Okay, that is a continuity. Okay, so we say preference relation is continuous if it is preserved under limits. Okay, so more precisely, suppose that we have two sequences of bundles. So x1, x2, generally xn. So this sequence approaches a limit point x. Okay, so there is some sequence of bundles. Okay, x1 is a bundle, 2 another bundle, and so on. So this sequence is approaching bundle x. And there is another sequence y1, y2, yn. So that approaches bundle y. Okay? And suppose that for each subscript, okay, and consumer thinks bundle x is better than bundle y. Okay, so bundle x is better than bundle y. Okay, so x2 is better than bundle y super 2, and x super n is weakly better than weakly better than bundle y super n. Okay, for every n, right? And this ranking, preference ranking, is preserved if the preference is continuous. Okay. So the limit point, the limit bundles, in case of limit bundles, bundle x, this limit point is better than the another limit point, bundle y. Right then, so preference ranking is preserved under limits like this. We say preference is continuous. Okay, so that is another assumption we need for existence of a utility function. So let me call this assumption 3. Okay? And assumption 1 was a completeness, and assumption 2 was a transitivity. Right. So the problem with the previous example, lexicographic preference, it violates this assumption, continuity. Okay? Because now if we think about these two bundles, okay, now we have to make a sequence of bundles. So this is xn, x super n, this is a y super n. Okay, so x super 1, now we put in 1 for n, 4 comma 1, y super 1, 3 comma 1. Okay, so because bundle x super 1 has a more of the first commodity than bundle y, so x super 1 is strictly better than y super 1. Okay, and x super 2 is going to be 3.5 comma 1, and y super 2 is a 3 comma 1.5. Okay, still x super 2 is better than, strictly better than y super 2. Okay, so for every natural number n, you can easily find x super n is better than y super n. Okay, now we think about the limit. So if we take the limit n goes to infinity, right, then x super n will approach 3 comma 1, that is x. Okay, and y super n approaches 3 comma 2 as n goes to infinity. Right? So now comparing these limit points, these two limit points, then limit bundle y is now strictly better than limit bundle x. Right? So the preference order is reversed under the in the limit. Right? So it is not continuous. Okay? So this is why. So this is the main reason for why. So this is the main reason why lexicographic preference has a no utility function. All right. So in the two next slides, we have a second representation theorem. It tells us preference relation. If the preference relation satisfies the two assumptions for rationality, so completeness and transitivity, and furthermore, it satisfies a continuity, all right, then existence is guaranteed. Okay, so given preference can be represented by utility functions, so we can work with utility function rather than preference relation. Okay, so before doing that, so we are gonna make another assumption on preferences. That is a desirability assumption. All right, so the idea is if all commodities are goods, okay, so all commodities available in the market are goods, that means the more the better, right? And it's natural to assume that large amounts of commodities are preferred to smaller ones. Okay? So that brings us this monotonous assumption. So this assumption tells us if bundle X contains more commodities than bundle Y, then consumer thinks bundle X is better. Okay, so this inequality, so when we compare two vectors, I think you guys know how to compare two real numbers, but when we compare vectors, say 1, 1 and 1, 2, Okay. For the first coordinate, these two vectors have the same amount. But for the second, this vector is larger than this one. Okay. Then we compare these two vectors with this inequality, right? But 2, 2 is strictly larger than 1, 1 for every component. Then we use these double inequalities. Okay. So, this inequality tells us if bundle X has a more of at least one commodity, right? Then bundle Y. Okay? And for other commodities, bundle X has a so let me say bundle X has at least more commodities than bundle Y. Then bundle X is weakly better than bundle Y. Okay? So 1, 2, because that has a more commodity of this, more of the second commodity, so that is a weakly better than this one. If preference satisfies monotonicity. Okay? Then we can define a strong version of this. Okay? And we say strongly monotone or strictly monotone. Then preference relation is strictly monotone if X is larger than or equal to Y, okay, and X is not equal to Y, okay, so X is weakly larger than Y, but X is not exactly equal to bundle Y, okay, because this inequality allows for the possibility that two vectors are exactly equal to each other, but we preclude that possibility, okay. Then consumer thinks bundle X is strictly better than bundle Y. Okay, so this is a Conley inequality. Then, we say preference relation is strictly monotone. Okay? So just the monotonicity requires weak preference, but strictly monotonicity requires strictly preference. Okay, so, one implication of this monotonicity is in case of two commodities, good 1 and good 2, and if we compare these 2 points, then say this is X, this is Y, then Y is clearly better than X. Okay, but we can't compare these two bundles, right? So these two bundles will be the ranking between these two will be determined by the exchange ratio. Yeah. So some consumers may prefer this one, or the other consumer may prefer this one. Yeah. It depends on the exchange ratio. All right. So one implication of this monotonicity is, if the preference is monotone, then indifference curve has a negative slope. So either under under M or SM, indifference curve has a negative slope. Okay? In other words, MRS has a negative value. Because marginal rate of substitution is so that indicates the slope of the indifference curve. Okay, so one more thing you can observe is monotonicity allows for the neutral good. So we say neutral good is the consumer does not care about the amount of commodity. So if the second good, if the second good is a neutral, then the consumer feels totally indifferent between these two bundles. Okay? So although one commodity, some commodities are neutrals, it does not violate monotonicity, but it does violate strong monotonicity, right? But if at least one commodity is bad, okay, so the more the worse. Then monotonous assumption, these two monotonous assumptions are naturally violated. Okay? So in case of, so if x2 is a bad, right? Then now indifference curve has a positive slope. Okay. So now we can't compare this x and y. Okay. But now we can compare these two instead. Okay. So this bundle is clearly better than this bundle. Okay. When x2. So the second good is a bad. All right. And then the weaker version of monotonicity is the next. There's a local non-satiation. So there is a little bit, generalization of the previous monotonicity. So we say preference relation is locally non-satiated if for every bundle there exists an alternative bundle y in the neighborhood bundle x such that consumer prefers bundle y, strictly prefer bundle y over bundle x. Okay, so it's a geometric interpretation is right here. So if we have just two commodities, so let me zoom in this. Okay, so if we have just two commodities, good 1 and good 2, okay, and randomly pick up one bundle, okay, we just pick up arbitrary bundle in this consumption set. Okay, and think about its neighborhood. Okay, so it's going to be an open ball. So inside this neighborhood, we can find a bundle y, some bundle y, that is strictly better than bundle x. Okay, so if the preference satisfies this kind of a property, then we say it is a strictly it is a locally non-satiated. Yeah. All right. So the more exact definition is, so for every x, so for every x and for every epsilon, positive epsilon, for every positive epsilon, there exists bundle y in the neighborhood. So neighborhood of bundle x. So x minus y. So its norms. Should I explain this? So that is a Euclidean norm. So in the two-dimensional space, this Euclidean norm indicates this open ball. Okay, smaller than epsilon. Okay, smaller than epsilon. So it indicates a open ball with a radius with a radius of epsilon. Okay, and such that y is strictly better than x. Okay, so there is a more exact mathematical definition of local non-satiation, but intuitively you may remember like this. Okay, so for every bundle x, in the neighborhood of this x, we can find a better bundle. All right. So here, bundle y, the alternative bundle y, that is strictly better than bundle x, does not have to have more of commodities than bundle x. Okay. So for this reason, local non-satiation allows for bads. Okay. So as long as we can find the alternative bundle that is better than bundle x, then it satisfies local non-satiation. So here, if we compare bundle y and bundle x, clearly bundle y has less of commodities than bundle x. Still, consumer may prefer bundle y than bundle x. Okay? So non-satiated preference, just excludes out the existence of a satiation point. There's a no satiation point in the consumption set. Okay? All right, and then another meaningful implication of this is a local non-satiation lures out thick indifference sets. Okay, so like this indifference set. Suppose that every bundle inside these two strips, okay, inside these two bands, all right, inside these two curves are indifferent. Okay, that it naturally violates local non-satiation, because if we just randomly pick up x inside this band, okay, then we can find there's some open bore. Then inside this open bore, every bundle is exactly indifferent to bundle x. So we cannot find the bundle y strictly better than bundle x, right? So it's violating. So it violates local non-satiation. Right. So another main implication is, indifferent set is going to be some curve in the consumption set. Okay. So lures out this kind of a thick band. Okay. And from the definitions of these three, monotonicity and strong monotonicity and local non-satiation, you can easily check strong monotonicity is the strongest assumption. Okay. So strong monotonicity implies monotonicity, and monotonicity implies non-satiation. Okay. So strong monotonicity even does not allow the neutral goods. Monotonicity allows for a neutral goods, but does not allow for bad, right? And local non-satiation, allows for even bads. Okay. All right. Then, so now we have the main theorem in this video, the utility representation theorem. So the previous desirability assumption is not necessary for existence. Okay. So under the three main assumptions, rationality and continuity, we have a utility function. But if we assume monotonicity, okay, then the utility function representing preference relation is increasing. Okay. And intuitively, if preference relation satisfies SM, strong monotonicity, then function U is going to be strictly increasing. All right, so I'm going to prove this statement. I'm going to prove this theorem in the supplementary video. Okay, so I think that is a little bit technical, and I think everybody has to know the exact proof. So just for those who are interested in the economic theory, I'm going to make a supplementary video and explain the proof. All right. However, the law of each assumption is intuitive, right? So continuity is necessary for existence and continuous utility function. So continuity of utility function, okay? And monotonicity is necessary for increasing utility function, okay? And rationality, we already talked about necessity of rationality. If the preference is irrational, we can't think of corresponding utility function, all right? And the major difference from the previous theorem, the first version of utility function or utility representation theorem, this result is independent of the characteristic of the consumption set. So no matter whether it is a infinite or finite, so whether it is a finite or infinite, under these three assumptions, we have existence of utility function. So that means, preference relation is not observed by analysts. We can see, people's preferences, but we know everybody has a taste. So every consumer has taste. Okay. So utility function, representing that preference relation is also unobservable. Okay. But under these assumptions, we can at least say some utility function exists representing, so that exactly captures a preference relation, one consumer's preference relation. Okay, and it has a nice property, there's an ordinal property. So we don't know what it is, but we know some utility function exists, and any monotone transformation is also representing the same preference. Okay? So preserved under monotone transformation. All right, so U has an ordinal property. Any monotone transformation also represents the given preference relation. Okay, so I'm going to prove that in the supplementary video. And then let me illustrate the convexity assumptions in the next video, okay? So hope you enjoyed this video, and I'll see you in the next.